Well, good afternoon. Welcome, folks. Welcome to session 151, Scaling in the Agentic AI, in the Agentic AI era with AI Hypercomputer. How's everyone doing? You guys had a chance to grab lunch? Yeah? Thanks for coming. The session happened to be competing with lunch. So, my name is Cheng. I'm product manager at Google. My team owns all the GPU-enabled AI infrastructure product on Google Cloud. I am honored to have two esteemed guest speakers joining us today. One is Balaji, who is the Chief Product and Technology Officer from Flipkart, and the other one is Sai from Baseten, who is the product lead there. Look, we know you're tired. It's day 3. It's lunch hour. Probably you're heading home after this. But we really, really appreciate that you're showing up here. And thanks for your trust and interest and curiosity in the subject with us, right? For that, I think everyone in the room deserves some sort of recognition or a certificate. I think this is perhaps a social media posting moment if you want to take a picture of that. But jokes aside, right? We promise that we'll make it worth your time and the extra caffeine by showing up here. I am, for one, super excited to hear the successful story from Flipkart and Baseten, how they are innovating in the agentic era and by building on top of Google Cloud. So I'm going to quickly cover what is AI agent, what are the challenges that you'll be facing with AI agents, and how Google Cloud can help. And then I'm going to invite Balaji onto the stage to talk about how Flipkart is optimizing shopping experiences by leveraging AI Hypercomputer. And then Sai will come up, and he'll be walking through how Baseten is accelerating their inference performance on top of Google Cloud. And then we'll wrap it up and answer any questions if there's any towards the end. So let's dive in. Agents are really enabling large-scale production of AI, right? And then notice that we're putting a focus around the outcomes versus the output, right? And then so what is AI application? AI application these days are really defined by containing one or more AI agents. Now, what is an agent? An agent is a service that's predominantly can really run autonomously with reasonings and then be able to execute tasks and also using tools and data, right? Just like any other services, they must meet compliance requirement, they must leverage CI/CD pipelines, they must follow security guardrails, right? And just like any other services, it also needs to protect or optimize for cost per performance benefits. It needs to be able to scale elastically. And lastly but not least, they also need to follow the security guardrails. That's a lot, but why don't we use an example to sort of illustrate what that looked like. Assume for a minute that you need to build an agent to help customer to respond to users' requests and generate a dynamic dashboard experiences and surface new insight. So what does this agent need to do? Step number 1, the agent needs to be able to parse the user inputs and build a plan. Step number 2, once you have a plan, then you need to be able to execute that, a sequence of actions by calling to different endpoints. This could be a simple LLM call to generate a code. It could also be a call calling into multiple MCP servers and pulling data from either a database on the back end or any other data sources. Finally, after all these data comes in, the agent needs to orchestrate and coordinate all these executions and summarize the results in a meaningful way to present that data back to the user, right? If you think about the components that enable all these operations behind the scenes, you can easily see that in this graph, the complexity involved in these execution can quickly becomes fairly overwhelming. And also the duration of each task can also vary quite differently. Some of the operations can be a long-running execution, right? And could be calling into reasoning models that calls into multiple MCP servers. And some of these tasks can be a short, large language model call for code generation, for example. Now, given all these complexities, right, we need to ensure that when you build your agents, you need to choose the best platform that provides three things. One, that can help you scale with a high elasticity. Two, you need to be able to right-size your compute to give you the best cost per performance. And three, also reaching sort of your performance latency SLOs. And three, you need to do all of this, right? Do all of this securely so that you can allow the agents to generate and execute code with the proper guardrails. So that was a mouthful. Let's try to summarize. What are the 6 characteristics of AI agents, right? Number 1, they need to be treated as untrusted. Number 2, they tend to be fairly bursty traffic. Number 3, many of them actually are latency sensitive. And number 4, some of them have long-running tasks. And number 5, and often they have idle cycles as well. Lastly but not leastly, if they're complex, some of them can be very memory hungry as well. Now, if you think about these characteristics, those 6 characteristics, what does that mean, or how would that introduce some of the challenges when you think about planning for your agentic infrastructure or applications? First, latency and throughput, right? So you need to make sure that the application can scale for elasticities in a world where accelerated resources capacities can be quite constrained. Second, compute efficiency, right? And so you need to make sure that we need to plan smarter ways that we use the compute to increase efficiency, at the same time reduce sort of the idle compute resources. Number 3, security and governance. Make sure that you apply security controls so that they are empowering the agents to handle long and complex tasks, at the same time ensuring access controls, debuggability, as well as auditability. So now, how can Google Cloud help, right? At Google Cloud, we build this AI hypercomputer architecture to optimize all AI and ML workloads and throughout the entire ML lifecycle stages. This happened to also address all the AI agents challenges as well. There are 3 major layers. On the bottom, you see is the purpose-built hardware. In the middle is open software stack framework. On the very top is the flexible consumption models. For the open software platform layer in the middle, building on a mature and a scalable platform like a GKE is very, very important, right? And not only because it's scalable by definition, but also has a native integrations with a lot of industry-leading framework like VLM for inference, like gvisors for agent sandboxes. These are important because then you, as the agent software owners or builders, you don't have to worry about integrating those things on your own, but you could rather focusing your energy and time and effort on building the logic, business logic instead. For the flexible consumption layer, consumption model like DWS, dynamic workload scheduler, would allow you to maximize and optimize your cost per performance, right? At the same time, allow you to scale your applications elastically. Now, on the bottom layer for the purpose-built hardware, at Google Cloud, we offer a variety of different hardwares that are all optimized for AI workloads, from TPUs to GPUs, from data center-wide AI optimized networking backend data center infrastructure all the way to AI-enabled or optimized storage solution. Specifically, for GPU-enabled products, we have a long-standing partnership with NVIDIA. And so we offer a full set of GPU-enabled offerings from Hopper generation to Blackwell generation, all the way to latest Vera Rubin products. Today, I'm going to focus on our G4, which is recently launched earlier this year, enabled by NVIDIA's RTX Pro 6000 product, which I believe is particularly interesting for agentic AI workloads. And the reason I think it's particularly interesting for agentic workloads is because I consider G4 as our Swiss knife sort of infrastructure product. Number one, it has a very versatile compute platform. In fact, the NVIDIA RTX Pro 6000 GPU is arguably one of the most versatile accelerator on the market. Number two, G4 product, we offer fairly generous memory, local SSDs, as well as network bandwidth configurations for the product. So it really offers enables a wide range of workloads. And then lastly, it comes with a diverse set of sizes, which I'll touch on in a later slide. But it basically offers from small all the way to large size that allows you to run different type of ML workloads. And for larger models, in particular, if you need to work with larger models, we also invested this capabilities called P2P, peer-to-peer network acceleration, that really improves, significantly accelerate the GPU to GPU communications. In a 4 GPU VM size, we observed 2 times nickel communication performance boost. In 8 GPU-based VMs, we observed 2.2x nickel performance boost. We'll talk about what it means for your workload performance in the next slide. And to turn it on, it's actually very simple. It's just an environment variable you need to set, and that's it. And we'll take care of the hard work behind the scene. Now, what does that P2P mean for your workload performance, right? So when you turn it on, we actually run a set of benchmark tests, and here are the results. When you turn on P2P, the darker orange bars are the P2P enabled test results. The lighter sort of graded orange color is the one without P2P. The XXL is basically the 3 different models that we run the benchmark test on. Llama 3 from 70 billion parameter all the way to 405B models. The y-axis is throughput, token per second. As you can see that you can observe up to 2.7x throughput improvements for larger models by using P2P. Similarly, when you look at latency, when you turn on P2P, you can observe up to 41% reduction in inter-token latency. In this case, the y-axis is for inter-token latency. In addition, we also partner with NVIDIA to enable vGPU support on our G4 product, which enables us to offer fractional GPU shapes. By the way, we're proud to be the first to market for vGPU support with NVIDIA. This would really enable you to standardize all your agents need in a single accelerator, right? And then you can just right size the compute to suit your sort of use cases. Now, also because we selected a more performant, a higher sort of performance CPU on the G4 system, this means is that you'll likely see performance boost out of the box, even for the fractional GPU shapes. And last thing I'll quickly point out is RTX Pro 6000 has an upgraded NV encoder core. So if you have decoding, encoding operations, you should also see significant performance improvement for those workloads as well. Now, remember the 3 layers hypercomputer, AI hypercomputer architecture on the open software framework layer. We have just announced the GK's Agent Sandbox support offering. This one actually includes 3 things. One is the managed warm pool support. The second one is default zero trust security posture. And lastly, it's very easy. There's a very easy to use Python API as well. Now, how does that help you with your agentic workloads, right? And so you can create up to 300 sandboxes per second, very high throughput per second per GK cluster, by the way, very high throughput. You can achieve sub-second time to first instruction latency, super fast. And when you use Axion, you can achieve 30% better price per performance from a cost-saving point of view as well. So highly, highly recommend you to give it a spin for your next agent project. Now, don't just listen to me. Let's welcome Balaji from Flipkart, Chief Technology and Product Officer, to talk about how Flipkart is optimizing shopping experience on Google Cloud. Welcome.
Thank you, Cheng. Thank you, Cheng, for introducing all the Google hardware innovations and the GK clusters. And I think a couple of things that Cheng talked about was one, latency and throughput, and also how do you use the compute more efficiently. And when you think about those two and put that together with the G4 RTX Pro 6000, we use a combination of these 3 to look at image synthesis and video synthesis workloads, right? So just going to the next slide, just quickly introducing Flipkart. We are the leading e-commerce platform in India. About 50% market share, 500 million customers, 200 million active users, billions of transactions. Almost the whole country is serviceable through our supply chain and logistics systems. We continue to grow, and our goal is to kind of serve the next billion that is coming online in India, right? We're primarily India-based. So today, when you talk about e-commerce, the primary engine or the primary piece of data that allows customers to discover what we have to offer is the catalog, right? And our catalog is huge, but there are a lot of other AI workloads that, as an example, we have laid it out here. One is the AI mode, which is the conversational commerce box that any customer or any persona for that matter in the e-commerce ecosystem can talk to get their jobs done. It could be finding something in our catalog. It could be returning something. It could be something around finding where the status of my order is, or it could be a seller trying to upload their listings to put it in a marketplace and so on, right? The AI catalog is a vehicle which shows everything in our marketplace. Sourcing and fulfillment, there are a lot of AI workloads like demand forecasting, inventory management, and of course everything has to be done in a secure way. Today, we are going to focus on the AI-led catalog use case, specifically around enriching shopping experience around image and video synthesis, and we'll talk about how we optimized our GPU workloads to make it better and scalable. And of course, also efficient and cost-effective. So this is what happens with our catalog today. We have about 50 million daily active customers who are querying our catalog. There are 150 million catalog items that are queried by these customers across multiple categories. And each and every catalog, when you get into that item, it could have multiple product views depending upon the different kinds of attributes the product has. And the customer behavior is, I'm looking for something, I find something, then I drill into it a little bit more to find out what that product is, and then I go through my shopping experience and eventually convert and become a shopper, right? And I buy things. Now the big thing here is catalog quality and catalog enrichment, right? So we'll get into that in a little more detail. So what is what happens in a catalog service, right? Or what does a catalog agent do? One is it is bringing in, it's ingesting millions of catalogs with attributes, and it's making sure that it is adhering to our overall systemic ontology. It is also adhering to our trust and compliance. It's also adhering to all the kind of taxonomy and pricing behaviors that have to be adhered to from the context of what a seller can do in the e-commerce ecosystem. So we ingest it there. Then we apply quality to it. And then there are two kinds of enrichments that happen. We do automatic enrichments of the catalog based on attributes, or the seller, in this case, can say, I need to enrich this catalog with an image of a person wearing a fashion accessory. For example, if they're selling a shirt in fashion, or a kurta, what do you call, in fashion, they could just upload an image of that particular fashion item, and they'd say, have a human actually wear this and show this particular image of the human in multiple environments, maybe in a playground, maybe in an office setting, or you can even do video synthesis, right? This is, we will show you a couple of examples where we have this lady who wears a kurta, all done by AI, and she walks from one place to other in motion, everything generated by the video synthesis models that we have. So, how do we do this? So here is the example of what we call image enrichment. All the seller did was the input image, which was the shirt, which looks like a Hawaiian T-shirt, and everything else was done by AI. So essentially, what happened there was the seller said, "I have this Hawaiian shirt, or this shirt that looks like I want to be on a beach. Can you have a model who is wearing this and has multiple, environments? He's walking in a street, or sitting somewhere, or standing in his house, looking out the window." Or you could also have the ability to actually convert those enriched videos into images where, the model is actually, walking. Now, all of this was done by AI. The only input was that particular image, right? So this is an image synthesis model. And then if you, there are multiple variations of that model, as you can see here, right? So, he was turning, here is walking in a street, that's inside a house, and this is just sitting, right? Different postures too. All of this, the AI image synthesis, models have to figure this one out. And it is that easy to do it, but then when you do this at scale, it can become very intense. It can become very CPU intense, memory intense, and it can also introduce a lot of latency into our systems, given the GPU capacity that we have. This is one example. Here is another example where the seller gave us two frames. The first frame of this girl wearing a top, and the last frame where she is, just turning away and walking. And everything in between that is showing in the output video was completely generated by AI. So this is a video synthesis model, right? It gives you a feel of how that dress might look on you when you're walking, right? So this is called catalog enrichment. Again, very memory heavy, very CPU intensive, right? So now if you take, so how did we do this? Now getting into the architecture elements of it. So like I said, there was an image, which was the shirt that was provided, and there was a prompt that was provided that, hey, have this image draped on a model in different environments and also create a motion video. So essentially what happened is we have the VIE encoder and the text encoder that is taken in, and it goes into a diffusion transformer model, and it goes through multiple iterations, about 4 iterations, and then once it is done, you have to decode it because it's compressed and then uncompressed, and then eventually you create the video frames. And this is a 5-second video frame that at 720p density. So it takes a good amount of time to do this in a minute or so, but it's very intense in the amount of memory and GPUs it uses. And we do this at massive scale, right? So we generate millions of images and millions of videos on a weekly basis. And our GPU capacity is what it is. As you know, acquiring GPU capacity is not that easy. Or if you want to acquire GPU capacity, you have to pay top dollar, and then in retail commerce, you can't afford to kind of break the bank on this, right? So we have to do it in an efficient way. So that's where we started talking to Google about how do we make this optimized that meets our needs at a cost and at a quality function that will scale also, right? So I'll briefly talk about what we did here. So one is, of course, we went with the G4, RTX Pro 6000. And we did kind of three levels of optimization. One is, we worked on increasing the parallelism for the diffusion transformer. And also we did the overlap sequencing for the VAP. That is, think of it like the application layer where we can do the parallelization. And then what we did was, we actually did some surgical, things around compilation and, custom architecting the media pipeline. So if you think about it, inside the G4, you have a media engine. So we did all the pre-processing and post-processing inside the media engine, and because it's sitting inside the GPU, the communication all happens within the GPU rather than from a CPU to a GPU. So that helped in terms of improving the latency. We started with using flash attention, and when we looked at the G4 and when we worked with Google, they said, why don't you use Sage attention? It's actually better and faster. And we also optimized the Blackwell kernel, the Triton kernel, And the kernel tuning is a tricky thing. You have to know what your workload is, and depending upon the kind of configuration parameters you give it, it can do a better job, or sometimes it even deteriorates. So you have to play with it till you get the right configurations. But these are all skills that one has to develop to figure out how to make the hardware work for you in a way that it is working fast and it's working efficiently. In addition, Cheng mentioned this. We used the Google P2P piece where the latency on the bus was much better than the traditional P2P capabilities that we got from NVIDIA. And as a result, when the bus is communicating faster, the GPUs are not idle, and you get better throughput and latency. So those are the big three things that we did. And the end of it, essentially what happened was we got 50% reduction in latency and 50% reduction in cost. And the cost reduction was quite phenomenal, especially at the scale at which we operate. And the throughput was also fantastic, because now with latency reduction, we can produce more videos. So essentially, that was one sort of optimization. The other sort of optimization, again, Cheng talked about this, is you can actually do virtualization, right? So what does it mean? For us is, depending upon the kind of AI models that we are using and we know the capacity that we need, we don't have to kind of block the full node, which in our case is an 8 GPU configuration for that one workload, and sequence everything behind it. So we used the MIG configuration to kind of break the virtualization of the GPU into multiple provisioning of GPUs for us. And the good thing about that is NVIDIA does a fantastic job of ring fencing and making sure that your workloads do work in parallel. And in this case, we achieved the model that could be hosted based on tuning went from 1 to 2. You can, theoretically, you can take it all the way to even 8, right, if you want. So that's what we did here. And what this did was, obviously, it reduced the cost significantly, because now I'm running 2 or 4 models rather than running one model after the other. Because when I do that, the GPU is not fully utilized, and it's, in most cases, it's actually idle. So I'm using all the idle time to parallelize all my work. So these are the kind of optimizations that we did. And I want to thank the Google team that worked with us very, very closely. And at the scale at which we operated, we're thankful that the understanding of the G4 architecture, the understanding of Google's software optimization on P2P, the ability to tune the kernels, and also using application level, model level efficiencies, like the parallel sequencing that we did and the VA work that we did, all put together got us to this point. And this is something that we will carry with us along the way and continue to improve. And as new families come, we'll build on top of the skill to make sure that when we think about AI, it's not only about the models, it's also about optimizing the models at multiple levels, including tuning the GPUs that we work with. So that was pretty much it. Thank you so much. I'm going to turn it over to Sai from Baseten, who's going to talk a lot more about this topic.
Thank you, Balaji. Hey everyone, I'm Sai. I'm a product lead at Baseten, and for those of you that don't know what Baseten is, we're a platform for training, optimizing, and serving your models in production. We run on top of GPUs. We run on top of Google Cloud and a few other providers, and we provide a lot of capabilities for running your own models in production, and a lot of capabilities to performance tune your models, as well as a lot of infrastructure capabilities like auto failovers, multi-region fallbacks, and also efficiently serving your models in production, which I'll talk about in a bit. But because we're here to talk about agents, I want to first start by talking about the different types of agents we see at Baseten. We have many customers that build agents in production, and I think they broadly fall into like a few categories, right? The first one is real-time voice agents. We all saw that on stage a couple of days ago about YouTube and NFL Sunday. And the thing that really matters here is latency. And I want to call back to what Cheng talked about earlier, which is one of the most important things with agents is latency and throughput. And you specifically see that with voice agents, where every millisecond or every couple of hundred milliseconds of requests and network hops really add up to what the end user sees, right? And this is one of the areas that we really help a lot of customers with. The second is like, the second big pattern is coding agents. And coding agents are really like, imagine it's like a barista taking multiple orders concurrently. So multiple requests per user, per session, across thousands of developers. How do you make that throughput really fluid and seamless for the end user? And the third one's like research agents, and these are mostly multi-agent orchestration across like multimodal type capabilities. You can think of multiple tool calls and chain together across various sets of use cases. And the thing that really matters here, again, is the same thing in the first two, but how do you make them fluid, and how do you make sure that for every tool call, things are extremely reliable as a model or as agents are putting these together. Across all of these types of agents, we have many customers that build these in prod, including Cursor, Abridge, OpenEvidence, many of these running on top of Google Cloud. And the one thing that's common across all of these agentic experiences is they fine-tune their own models. So if there's one big takeaway that I have for all of you here today is that if you have any proprietary data and you're building these agentic experiences, I think it's really worth considering what you can fine-tune and how you can fine-tune it. And obviously it was a lot harder back in the day, but I think the barrier of entry is a lot easier and better now. And I want to talk a little bit about the types of problems that we solve for customers and we end up seeing. Google Cloud provides a very strong, reliable layer of infrastructure for us to build on top of. And as these companies and customers come to us, we help them figure out how do you take the models that you've fine-tuned, deploy on top of providers like Google Cloud and GeForce, and serve these in production to their end users. So like the first problem with getting your model onto the GPU is latency. A very clean example I'll give you is customers bring us their fine-tuned models, and generally your model might be like tens to hundreds of gigabytes, right? And you're having to take the model weights from storage, traverse it over the network, onto the machine, into the GPU. That might take anywhere from tens of seconds to multiple minutes, right? So one of the things that we built is this concept of distribution delivery network. We call it the Baseten delivery network. And it's very similar to how a traditional CDN might work, right? Back in the day with web, when a user did a request, it might take them multiple minutes to get served that content. And it's very similar with model weights, but at a very different scale. So we built this thing that helps you stream your model images or model weights onto the GPU. And a lot of our customers see like a 2 to 3x improvements in cold start use cases. The second thing is one serving approach is not going to solve all different modalities, right? You have LLMs, you have diffusion models, voice models, and we have a fantastic model performance and FDE team that embeds with a lot of our customers, many of them that are running on top of Google Cloud, to build and serve these models into production and fine-tune them to fit their benchmarks, whether it's like latency requirements or model performance requirements. And the third one is, building and shipping and operating in production are just like vastly different things, right? Like you can build and ship and have a prototype, something that runs in beta, something that's like relatively straightforward. But where it gets really complicated is how do you scale this and how do you serve it across multiple clusters in multiple regions, serving multiple concurrent requests. An example might be a very common thing that, a very common use case is A/B testing different model versions. What happens when one model version goes down? So the stuff that, the abstractions that we built on top of Google Cloud, an example might be like active-active, where you have 2 model versions running in different regions. Baseten automatically takes care of like falling back to a different region without any downtime for your end users. So from an end user perspective, they're not going to see this failures, and you don't have to worry about dealing with those types of things. Cool. Now, at Baseten, we kind of think of this as like an end-to-end pipeline for how you serve inference and how do you serve these models. And the way we're thinking about this is that for every layer of the stack on top of what Google's building with Hypercomputer, we're providing these very inference-specific optimizations. So if you have a model that you're trying to serve and build use cases on top of, we can make that extremely easy for you. And we have many customers that build on Google Cloud and Baseten. One example is Hebbia, who's building this research agents where they have almost a 2.5x improvement in their tokens per second throughput and a 4x improvement in the time to first token, which really makes a difference when end users are using this. But the big thing that I think everyone cares about is cost, too. A 10x difference in cost is non-trivial. As far as like where we're headed, a lot of why we're able to move fast is because of the innovation that's happening at the infrastructure layer, both from a reliability standpoint and the set of primitives that, with things like AI Hypercomputer. A couple of areas that we're really investing in is we do have a lot of research that we end up doing. One example that we most recently released is how do you extend context windows in the fine-tuned models that you bring to us. I can share this out later, but one of the most recent research papers we released, we saw like an 8x increase in KV cache compression, which leads to significantly higher context windows for the models that you bring to us. Baseten delivery network is the same thing that I mentioned, but one primitive that we're going to take the same primitive and make it really easy for you to build ephemeral agent use cases on top of things like the sandboxes that Cheng mentioned earlier. And also, what we're trying to really invest in is very similar to how we built this Baseten delivery network. How do we build more primitives around agents to co-locate them near your GPUs? Because at the end of the day, the thing that really matters is how are we optimizing for latency and throughput. I want to call Cheng back onto stage to wrap it up, but I want to quickly give a call out that a lot of how we're able to move fast is because of this really cool innovation that's happening at the infrastructure layer that Google's doing. So thank you. Thanks.
Thanks, Sai. Wow. 2.5x improvement on token throughput and 4x on time to token, first token. That's really impressive. By the way, if you remember from Balaji's talk, Flipkart was able to reduce 50% of their latency at the same time reducing 50% of their cost, right? That's also amazing. Also, I heard that Flipkart was able to create 60% of new experiences with zero touch, right? Amazing results. Let's wrap, right? So what have you seen so far in the session? We talked about what are the AI agent challenges. We talked about how Google Cloud can help. You heard from Flipkart on how they are optimizing and innovating shopping experiences by leveraging AI Hypercomputer. You heard from Baseten on how they're accelerating inferencing experience by leveraging Google Cloud. Now, if there's one slide to take away, I would recommend this slide, right? And this basically, this is it. This is our 3-layer AI hypercomputer architecture with purpose-built hardware in the bottom, open software framework in the middle, and flexible consumption model on the top, right? So thank you all for sticking with till the end. We really appreciate your active engagement. And remember, you earned the next day 3 survival certificate.